Hey, what's up, guys? Yeah, so today I want to talk about a new results. Sorry, not new results, a new topic in the analytic number theory called the partition. And today I will also give one proof of Euler Pentagonal theorem. So hope you guys subscribe to my channel. If you haven't seen my analytic number theory video lecture, that I will post link below so you can check it. Okay, so let me just talk about partition. Okay, so partition is an interesting topic. So and also very crazy. So let me just define P of n to be the number of ways. So number of ways. So number of ways to separate or the partition. Partition n into integer, positive integer in n into positive integers into sum of the positive integers. Okay, so the idea is that we want to write n into the sum of the different integers, and we want to count the number of ways. And there's no permutation. So we are not, so for example, the 2, 1, 1, I would say it's the same as 1 to 1. Okay, so let me just quickly see some simple example. So for example, P of 4 is 5. Okay, because I can write 4 is 4, and I 3 plus 1, or 2 plus 2, or 2 plus 1 plus 1, or the 1 plus 1 plus 1 plus 1. Okay, so you can see that there is 5 ways. Let's consider P of 5. Okay, so I can write 5. I can write 5 and 4 plus 1 and 3 plus 2 and 3 plus 1 plus 1 and what? And 1 plus 1 plus 1 plus 1 plus 1 and 2 plus 2 plus 1 and also what? And also 2 plus 1 plus 1 plus 1. Okay, so there are 7 of them. So P of 5 is 7. Okay, so question. So the question that I will answer after maybe the next video is that mathematicians try to find the asymptotics of this P of n. Okay, so I mean, you can say, oh, P of n can be easily computed. Maybe you write computer code, but how do you find the P of n asymptotics? So for example, one might guess that the P of n should be exponential in n, but maybe some coefficient here divided by some strange function here. Also, this is an interesting topic. Okay. So theorem that I will, this is very simple observation is that the generating function of partition. Okay, so it's like this is a theorem is that if you take m from 1 to infinity, you write 1 divided by 1 minus xm will be the generating function of the partition. Okay, now this proof is very simple. So the rigorous proof need to take care about the convergence, but then we just using a sloppy proof. Okay, sloppy proof is that then we just restricted x to be lesser or equal to 0 to less than 1 because there's just some convergence issue. But if you don't care about convergence, then fine. You just write 1 minus x into 1 plus x squared. So you can see that you get 1 plus x squared, 1 plus x cubed, x squared, x fourth, x6, 1 plus x cubed, x6, x9. Or equals to this. So you can see that so let's say the right hand side contribute n, and at least somebody maybe in the left side there's a xk1 contribute, maybe in this side there's a 2k2 contribute. So 2k2 means that there's x2k2 for some particular integer a positive integer k2, and also there's xk3, 3k3. So you get 3k3 maybe it's mkn. And then equals to x to n. So this gives you n is equals to some. So there's a so means that we want to find the the pair such that k1 up to km. So m can be arbitrarily large, and all these are greater or equal to 0, such that n equals to k1 plus 2k2, 3k3, up to nkm. So which is exactly the definition of partition. Okay, so P of n, just P of n, right? Because in P of n, I don't care about permutation, so I only care about how many 1, how many 2, how many 3. That's it. Okay, so let me talk about the Euler Pentagonal theorem. Okay, so this theorem is also amazing. It's very weird. Okay, so the fact is that okay, so let me just quickly introduce the pentagonal number. So I previously have a video discussing the pentagonal number or the polygon number, but it's very elementary, so you can check out. So pentagonal number omega n is defined to be 3n squared minus n divided by 2. Okay, and the and the mathematical meanings that suppose so for n equals to 1, you get 1. For n equals to 2, you get 5, because you have a pentagon. So get 5. And for n equals to 3, you can draw a large pentagon. Okay, which is each side. So you can imagine there is a pentagon and each side has 3. Okay, so you can see that it's this. Okay, so there's a 1, 2, 3. I guess it's a 1, 2. Yeah, so it's 1, and you can check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe I missed something. Oh, sorry, I'm stupid. This is not true. So where I should draw. Sorry, yeah. So I'm stupid. So each side should be 3 of them. Sorry, so I need to do expansion. I need to do this. Right, so get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so yeah, so you can check it. So simply prove to be 3n squared minus n divided by 2. Okay, this is called a pentagon number. Okay, so the question why pentagon number is related to Euler. Okay, so this is the Euler Pentagonal theorem. Says that if you do the 1, you do the say n from and let's say you get n from 1 to infinity, and do 1 minus xm. So this will be summation of this. You just do the reciprocal of the partition. Will be very weird results. Will be 1 plus minus 1 to n x omega n plus x omega negative n, n from 1 to infinity. This is, or one can write n from negative infinity to infinity minus 1 to the n and the x omega n. So if you do expansion, you get 1 minus x squared plus x5 plus x7 minus x cubed, 12 minus x15. Okay, so it's weird that if you do the inverse of the partition, that you get the power which is related to the pentagon number. Okay, basically it's the omega n and omega n omega minus n. Okay, so this is yeah, this is weird. You can prove this. This is really interesting. Okay. And amazingly, if you do this, right, if you do the expansion, that you can you get some Okay, so maybe yeah, you can check for n equals to 1, you get -1, right? Omega 1, omega -1 is both 1. And another is that omega is 5 and 7. And then there's a 12 and 15. Okay, so you get two pair of 2, which just come from here, which is a pentagon number. Okay, and the omega, sometimes omega -n is also called pentagon number, just this. Okay, so this is a weird result. Because why inverse of partition is related to the pentagon number? Okay, so there are three kind of proof. One is that I will talk about today is analytic results. So analytic way. So this way is a little bit boring. And another proof that I will talk about in the future is the combinatorics. And then there's a third way called the you can use the modulo function. So it's a powerful big machinery. So it's a Jacobi triple inequality, triple identity. Okay, this is really a little bit difficult. So I will talk in the final video. Okay, so yeah, let's go to a proof. Okay, so in order to prove this, let's write P of n to be, let's say, n from 1 to infinity. Or maybe at r 1 minus x to the r. Okay, so r from 1 to n, 1 minus x to the r, and let me define s of n. Okay, so s of n definition will be a little bit weird. So 1 plus r from n 1 to n minus 1 to the r, and x omega r plus x omega negative r. Okay, so the only thing I need to prove is that the Pn minus Sn goes to 0 as n goes to infinity. Okay, so this is the key point that I want to prove. But this is so I will prove the following. So I claim that the Pn minus Sn is bounded by n plus 1. Okay, so since I know that x is less than 1. So this, when n goes to infinity, then this guy goes to infinity. So we'll prove this. So this is what I got to prove. Okay, so let me define f of n is another function, which is r from 0 to n minus 1 to r, Pn divided by P of r, x Rn plus G of r. Okay, and then let me define G of r to be the triangle number. So it's r times r plus 1 divided by 2. Okay, so this is weird, right? So Pn is here, and I put Pn divided by P of r from 0 to n. So this guy will give me another polynomials, and that times xRn times plus G of r, and I define f of n. Okay, so simple exercise. It's very simple to check that f1 equals to s1 is 1 minus x minus x squared. I mean so check for S1 is trivial. Also, you need to check for F1. Okay. Okay, so now let's go to the next. Okay, so there's lemma. So lemma is I want to say that Fn minus 1 is Sn minus Sn minus 1. Okay, so once I prove this lemma, since f1 is s1, right? So if this lemma is true, then what I'm going to say is that fn equals Sn for every n. Okay. So let's imagine that this lemma is true. Okay, so let's do a quick way. So suppose this is true. So let's just write down. So suppose lemma is true. Then I can write Fn equals to, so this is Fn, right? So there's a Pn. Pn stands for r equals to 0 term. So when r equals to 0, you get Pn. Okay, so you get Pn plus r from 1 to n minus 1 to r, Pn divided by P of r, x Rn plus G of r. Okay. And then you can easily check that 6, right? So this Pn, since r is less than, so Pn divided by P of r is less than 1, greater than 0. Okay, and yeah, this is true, right? Because you get 1 minus x and their product of them. And also you can check that x Rn plus G of r is less or equal to xn minus 1. Maybe for this one you need to think a little bit, but you can check this because this is nr plus r times r plus 1 divided by 2. Okay, and 6, right? So this is this one, right? Okay, so and the x is, so remember that x is less than 1. Okay, so this, if you have more x, then this will be small, right? So you can check that when r equals to 1, then this term should be the maximum. So when r equals to 1, you get n plus 1, right? So which is less or equal to x n plus 1. Okay, so once you have these two, then obviously that x fn minus pn is bounded by x n plus 1, right? There are n terms of it, so there are n term. Okay, so n times x n plus 1. Done. Okay, so if this lemma is true, then the simple analysis will give you results, and you prove since fn equals Sn, so it's Sn minus Pn is bounded by n x n plus 1. So just take n to be infinity, then you prove the Pentagon, you prove all the Pentagon theory. Okay, so let's start to prove the lemma. Okay, so the lemma is this, right? So what we are saying is that this Pn looks like this as n of this, and then I define this f of n, and I want to claim. So the lemma is very simple, that we want to prove that fn minus 1 is Sn minus Sn minus 1. Okay, and yeah, let me just write a definition down so that we can do step by step. This calculation is not difficult, but a little bit tedious. So let's do step by step, and hopefully I explain the detail. Okay, so fn minus 1 equals to summation r from 0 to n minus 1 to r pn pr x r n plus g of r minus r from 0 and minus 1 to the r pn minus 1 pr x r n minus 1 plus g of r. Okay, and let's write this pn into 1 minus x to the n pn minus 1. Oh, this is very simple, right? This is just a definition. Okay, so we get r from 0 to n minus 1 to r, and 1 minus xn pn minus 1 xrn plus g of r divided by p of r minus r from 0 to n minus 1 to r pn minus 1 p of r xrn minus 1 plus g of r. Okay, so we get two terms. We just split. Okay, so very simple. We just split. Okay, so we just split. Okay, so we split and separate r equals to n. Okay, so we separate this into this one minus n to the xn squared plus g of n. This is the r equals to n term for the first one, and then we do a separation. So we get r equals to 0 and then n minus 1, and then we separate into two terms. One is minus 1 to r, pn minus 1 divided by p of r. Okay, so the one term xrn plus g of r minus r from 0 to n minus 1 minus 1 to r pn minus 1 p of r x. So this term is xn, right? So we get r plus 1 n plus g of r. Okay, so this is the first term. This is the first term, right? These all three terms come from the first term because we separate these two, and then minus r from 0 to n minus 1 to r pn minus 1 p of r x r n minus 1 plus g of r. Okay. Okay, so now let's see. Okay, so let's do the observation. So we can see that this term and this term looks exactly the same, right? Because we get n minus 1 p of r. Okay, so we can just combine these two. Okay, once we combine, we notice that when r equals to 0, then these two terms cancel. These two terms is exactly 0. If r equals 0, that you can see that when r equals 0, then these two terms is exactly the same, right? So you can just cancel. So we combine these two terms. Let me just write down. We get minus 1 to n x n squared plus g of r. Okay, plus summation r from 0 and minus 1 to r. So r equals to 0 turn cancel. So let's change r equals to 1. And combine these two, p n minus 1 p of r, and x r. So we can pull out x n minus 1. We can pull out this plus g of r, x r minus 1. Okay. Now let me preserve this term. P n minus 1 p of r x r plus 1 in plus g of r. Okay. Okay, so this term, let me just shift index, right? Originally, I write r plus 1 n g of r. I changed r to 1 to n. So let me just change this. So let me just shift index. So I change the index from r1 to n. And then once I do this, this may need to be r minus 1. And this need to be r minus 1. And this need to be rn plus g of r minus 1. So let me just change this. Rn plus g of r minus 1. Okay, so now we have these three terms. Okay, so now using your eyes, and you can see that these two terms has the beautiful relationship. Okay, so let me just check. Let me just check to lemma. So check what? Check what xr minus 1 divided by p of r will be minus 1 divided by p of r minus 1, right? This is trivial, you can, by definition. And also this rn minus 1 plus g of r will be rn minus 1 plus rr minus 1 divided by 2, which is exactly rn plus g of r minus 1. This is simple, right? Just nr plus r minus 1 r minus 2 divided by 2. So we just shifted this minus r into these terms, then you get this. Okay, so we have this and this. Okay, so now you can see that this p n minus 1 divided by p of r minus 1. You can see that these two terms, right? So you can see that these two terms is exactly the same. Okay, exactly the same, because this power term is actually this power term. Okay, and then you get, if you this xr minus 1 divided by p of r, which is xr minus 1 divided by p of r, will give you minus 1 p to r minus. So you can see these two terms cancels, and the remaining term is that r equals n term. Okay, so final results will be minus 1 to n, the first term, plus minus 1 in x n squared plus g of n minus 1. This comes from r equals to n term. Okay, so if you put r equals to n term, okay, you get this. You get this. Okay. Okay. So now what? Now let's pull out this minus 1 to the n, and you get x omega n. Remember, this omega n is 3n squared minus n divided by 2, and omega negative n is 3n squared plus n divided by 2. So omega n is actually n squared plus, sorry, this is r equals to n. Okay, so it's g of n. This is n squared plus g n minus 1. Sorry, this is g of n. Okay. Sorry, this is. This omega n 3n squared minus n divided by 2 is actually obviously is g of n, which is n divided minus 1 divided by 2 plus n squared. Okay, and for this one, minus 2n squared minus, yes, this should be Yeah, this should be should be n squared plus g of n minus 1. And for this one is larger, so it's n squared plus g of a. Okay, so this term is omega negative n. This term is omega n. Okay, so remember what's this s, right? So it's Sn divided by this. So obviously that this term, right, is actually Sn minus Sn minus 1 equals to minus 1 to n x omega n plus x omega negative n. Okay, so we prove, right, this term is actually this. Okay, so since that's the proof, right? So this prove the Pentagon theorem, the Euler Pentagon theorem, because the lemma, we have this lemma and we know f1 equals s1, so f equals to Sn for all n, and the previous lemma will give you will give us the Pentagon theorem. Okay, so let me give you a quick application. Okay, so this application also very strange. Okay, so this is so-called Euler recursion formula. Euler recursion formula for P of n. Okay, so we know that let's define P of 0 is 1. And let's say P of 0 is 0 for any n less than 0. Okay, then we have P of n equals to P of n minus P of n minus 1 minus P of n minus 2 plus P of n minus 5 plus P of n minus 7 minus equals 0. Okay, or simply speaking is that we have P of n equals to summation k from 0 to infinity minus 1 to the k plus 1, P of n minus the Pentagon number plus P of n minus omega, the Pentagon number. So it's like this. Okay. So obviously that you can check. The first pair is 1 and 2. The second pair is 5 and 7. And the next should be 12 and 14, I think so. Oh, sorry, 12 and 15. Okay. Okay, so proof is very simple, right? Proof is trivial. So proof is trivial, right? The reason is that we already know the Pentagon theorem. So what we can do is that we just that summation 1 over Pn xn, and from 0 to infinity. This term will give you, we got summation, sorry, P of n xn, and from 0 to infinity. So these results will give you the Pentagon, right? So this guy will be the Pentagon theorem. So it's 1 plus minus 1 to the k x omega k plus x omega negative k from 0 to infinity. This term times summation P of n x n, and from 0 to infinity will give you 1. Okay, so which means that this term times this term will give you 1. Okay, so we just expand P of n. So you can see that this is the just 2-power series, and then if you take any results for n greater or equal to 1, then you get 0. Then the P of n will automatically have the recursion like this. Okay, so you just times this and use the Cauchy product. It's trivial. Okay. Okay, so once you have this, then you can build, right? You can solve the higher P. Okay, because now previously you need to count 1 by 1, but now you have this powerful theorem that you can solve, right? For example, you can find like say P of 10. You can solve this. It's 42. Maybe hard to solve, but you can solve it, and you can keep going. So you can find a lot of it. Okay. The very weird results that we will prove in the next video is that due to this, that so basically this P of n has the first asymptotics which conjectured by Ramanujan is that P of n looks like this. Maybe it looks like exponential k square root of n, where k is pi divided by 2 divided by 3. This is very weird, right? So how can one find one find this? Okay, and actually P of n has this kind of formula. for n square root of 3 as n goes to infinity. Okay, so this is very difficult. Yeah, this is very difficult to prove. But in the next video, so in the next video, that I will give the simple proof of the upper bound. Okay, so one can use the Euler Pentagonal theorem to prove that P of n is less than exponential pi divided by square root of 2 divided by 3n. Okay, so how can you find this kind of proof if you don't know about this Pentagonal theorem? Okay, so that's it. See you guys next videos.